Hello everyone, today we're going to be going over the June 2023 Physics Regents exam. In this video, we're going to be looking over Part A, which is the first 35 multiple choice questions of the test. For this video, if you want to follow along at home, the link to this test will be in the description of the video alongside the reference table that I'm going to be using to solve this. So number one asks us which pair of quantities are both scalar quantities. When we're talking about scalar quantities, we're talking about quantities that have no direction. And you'd be asking me, how can a quantity have direction? Well, think about velocity, right? Whenever you're dealing with a physics problem that has velocity, you're always going to have a direction associated with that. So for example, a car is traveling at a velocity of 25 meters per second east, right? A spaceship is heading 25 meters per second north, right? So those type of units that do have direction are called vectors, right? And vectors are velocity, momentum, force, all these type of things that you need to specify in which direction something's acting, right? So for example, force is a vector because you need to know what direction the force is going in, right? You can't just say a 20 Newton force is exerted onto what? On which direction? To the left, to the right, right? So what I'm trying to say is that a scalar quantity has no direction associated with it, which means that our answer is going to be number one. Speed has no direction associated with it. Speed and velocity have the same number, right? But speed does not have a direction associated with it. When you look at the speedometer on a car, right, it's going to tell you how fast you're going, right, your speed, but it's not going to tell you the direction that you're going. And the same thing with mass, right? Your mass is how heavy you are. So for example, if I'm 60 kilograms, right, I am 60 kilograms, right? There's no direction that goes with it. Number two is wrong because momentum has direction, right? You have momentum in a direction, right? You run. If you run forward, then your momentum is forward, like it's in that direction that you're running in. Momentum and displacement has direction, right? It's by how much you moved from your starting point and where you moved from your starting point, right? And four is wrong because displacement, once again, is a vector, right? So number two says, in an attempt to get ketchup out of a bottle, a student takes off a cap, turns the bottle upside down, accelerates it downwards, and then suddenly stops it. Ketchup is released from the open bottle because the ketchup does not stop moving when the bottle does. The ketchup leaving the bottle illustrates what? Okay, so let's draw out this scenario. Here we have our little ketchup bottle, right? And inside of this bottle, it's obviously filled with ketchup. So what the student does is he grabs this bottle with his hands and he accelerates this bottle downwards, right? He thrusts it downwards. And as he thrusts it downwards, he stops thrusting it, right? So he just shakes it down and stops halfway down. And what ends up happening, right, is the ketchup continues moving downwards and out of the bottle once he stops moving it. So this is going to exhibit the rule of inertia, right? What is inertia? Inertia states that objects that are in motion tend to stay in motion, and objects that are at rest tend to stay at rest. Here, once you start pushing this ketchup bottle down, you make the bottle go down, right? The bottle is in motion, and then everything inside of the bottle is also in motion. And then all of a sudden, if you stop making the bottle go down, the bottle is going to stop, but the things inside of the bottle are going to continue to want to move downwards, right? So an object that is in motion, which is the ketchup inside of the bottle, is going to have a tendency to continue staying in motion, which means that it's going to come out of the bottle, right? Resistivity is wrong because this has to do with electricity. Resonance is wrong because with resonance, you would have to have a frequency and waves. And there's no frequency here, so it can't be resonance. And four, mass being converted to energy is wrong because the ketchup bottle isn't changing in mass or being converted to energy. Number three says the same net force is applied to object A and object B. The mass of B is 3 times greater than the mass of A. Compared to the acceleration of A, the acceleration of B is what? Well, here we're dealing with net force, which is F net, and we're dealing with mass, and we're dealing with acceleration. And we're trying to find acceleration from F net and mass. So let's look at our reference table and let's see if we could find a formula that has those terms. Here, we found it. Acceleration is equal to net force divided by mass. So if acceleration is equal to the net force divided by mass, let's just plug in numbers and see what happens. Let's say that object A has a mass of 3. So object A is equal to 1 kilogram. It's 1 kilogram, right? That means that the mass of object B then has to be 3 kilograms. And if the same net force is applied to both of them, let's just say that the net force is 1 newtons. Okay, so let's just plug these fake numbers that we made into our scenario, right? If object A, a 1 newton net force is applied to object A that weighs 1 kilogram, our F net is 1 and our mass is 1, so our acceleration is 1. So our acceleration for A is 1. Now, let's do the same for B. Our F net is going to stay the same because it's the same force, but our mass is now 3. So our acceleration is actually going to equal to 1/3. And here it's asking compared to the acceleration of A, the acceleration of B has to be 1/3 as great. Number 4 says, what is the mass equivalent of 3.37 times 10 to the negative 19 joule? So here, joule, we're dealing with energy. This is the unit for energy. And here we're trying to find a mass equivalent. And this is making me think, well, how can I find mass from energy? Let's look at a reference table for something that has mass and energy. So we're not going to be in mechanics. This is actually going to be in modern physics. And this is going to be the equation E equals mc squared. So E, which is our energy, is equal to mass times the speed of light squared, right? How do we know this? Because we're dealing with mass and this is energy. So really what you have to do is you have to solve for m here. So 3.37 times 10 to the negative 19 has to equal to our mass times the speed of light, which you can find at the top of your reference table squared. So this number squared, right? And if you plug this into your calculator, you end up getting choice 2 as your answer. Number 5 says, which object is in equilibrium? So what is equilibrium? Equilibrium is when when the net force applied to an object is equal to 0, right? So everything is balanced out. And this could mean that either the object is just sitting down, not moving, or that the object is moving at a constant speed. Let's illustrate this, right? Let's say that I have a box here and I have a person pulling on this box with a force of 5 newtons. This box is not in equilibrium because an unbalanced force is being applied. Now let's say all of a sudden that I add another person who's pulling in the opposite direction with 5 newtons. This is now in equilibrium because the force is balanced. This is positive 5 newtons, this is negative 5 newtons, right? Because it's in the opposite direction. So when you're looking for an object in equilibrium, you're looking for something that has no net force being applied to it, which means that choices 1, 2, and 4 have to all be wrong. The Earth orbiting the sun, whenever you orbit something, you're in a constant free fall, which means that gravity is impacting you, right? Gravity is pulling you down, and there's no force acting against that gravity, so it's unbalanced. Number 2, when you throw a baseball at its highest point above the ground, once again, gravity and air resistance is acting on that ball, right? So the force is still there, even though at the highest point your velocity may be 0. The gravity is always constant. It's 9.81 meters per second squared, right? So it's still going to be acting on that ball. And number 4, a bicycle skidding to stop. If you skid to stop, if you're stopping, that means you're decelerating, right? Which means that there's being a force applied backwards to the direction that you're traveling in. And that leaves us with 3 as the right answer, because if a car moves at a constant speed, that means it's not being accelerated or decelerated. That means that the force being applied to the left of it, or to the left of its path of travel, is equal to the force to the right of it, right? So if there was a 5 Newton force here and a 10 Newton force here, the car would be decelerating if it's traveling in this direction. If this was 10 Newtons and this was 5 Newtons, then the car would be accelerating, right? But if both of these newtons are both 5, guess what? The car is traveling at a constant speed and the forces cancel out, right? So think constant when you think equilibrium. Number 6 says a race car travels around a flat circular track at a constant speed. The net force on the car acts what? Well, here we're traveling around a flat circular track, right? So we're going to think about centripetal force. This is going to be the center of our track. And let me just draw my track right here. And let me draw my car right here. So it's traveling around this circular track, right? And with any time you have centripetal force, right, it's always going to be perpendicular to the velocity. So if our car's velocity is pointing upwards, then our centripetal force, or our FC, this is our V, our FC is going to always point to the center, which means that the choice is number 1. It's never going to be parallel. The net force on a car will never, ever be parallel. It's always going to be perpendicular to the velocity toward the center. Right? It's never going to be from the center. It's always going to be toward the center and perpendicular, right? So no matter where you draw this, let's say even if the car was here, you're always going to have a 90-degree angle between the velocity and the centripetal force. So number 7 says an object is traveling in a horizontal circular path at a constant speed. If the radius of the path were doubled while the speed remained constant, what would the centripetal acceleration be? Right? So here we're dealing with centripetal acceleration, so it'll probably be important to know the formula for this. So if we scroll down to mechanics, and we see that AC, and if you don't know what AC means, you could always look for the letter here. AC stands for centripetal acceleration. Centripetal acceleration is equal to v squared divided by r. So let's just write that down, v squared divided by r. And now let's see what happens. If the radius of the path were doubled and the speed remained constant, what would happen? Let's say our velocity was equal to 1. And let's say that our original radius is equal to 1 as well. V squared, that's 1 squared divided by r, which is 1. So originally, we would have a AC, or a centripetal acceleration, of 1. Okay. Now, let's see what happens when we double this radius. Now, all of a sudden, our radius is 2, right? So 1 squared is 1, and r is 2. So now, our centripetal acceleration is 1/2. So in other words, we have it because we're dividing our velocity by a greater number. So it's going to be decreased by the number that we increased, if that makes sense. So number 8 says a 600 Newton student pushes on a vertical wall for 20 seconds with a constant force having a magnitude of 100 newtons. What is the magnitude of the force that the wall exerts on the student? Here, we're talking about a kid pushing against a wall for a certain amount of time, right? This is the guy, and here he's pushing against this wall. He's pushing against this wall with a force of 100 newtons. And because of Newton's third law, the wall is then pushing back at the kid with 100 more newtons. So the choice has to be 3. Newton's third law states that every action has an opposite and equal reaction. So in this case, the student's action is the 100 newtons being placed on that wall. And the equal and opposite reaction is the wall pushing back 100 newtons at the kid, right? So always think about that. The only thing that mattered here is the force that the kid was exerting on the wall, which was 100 newtons. So number 9 says an unbalanced force of 20 newtons. And notice how here we're dealing with an unbalanced force. Here we're dealing with equilibrium. So equilibrium is when the forces are balanced. But either way, an unbalanced force of 20 newtons is applied to a mass of 1.0 times 10 to the third kilograms. After 10 seconds, the momentum of the mass will have changed by what? So here we're looking at a change in momentum. And because we need to calculate something, I'm going to go ahead, I'm going to look at my reference table, and I'm looking for force, or F, or F net, and something that has to do with momentum, right? So here I'm going to scroll, and as you can see here, momentum is represented by a lowercase p, and delta is going to be represented by change. So if I'm looking for change in momentum, I'm really just looking for delta p on my reference table. And here I just found it. F net times t is equal to delta p. So F net times t is equal to delta p. And delta just stands for change in, and p stands for momentum. So all I have to do to solve this problem is just plug this in. Our net force is our unbalanced force of 20 newtons, right? Multiplied by our time, which is 10 seconds. And this is going to equal the change in momentum of 2.0 times 10 squared kilograms times meters per second, right? Which is choice 1. So then number 10 asks us to lift a heavy block off the floor. A student pushes with force F on a rope that passes over a pulley as shown in the diagram below. Which pair of vectors represent the perpendicular components of the force that the student exerts on the rope? So here we have a force vector, right? This vector is going to be the sum of 2 vertical and horizontal components, right? Because look, this guy isn't pushing all the way horizontally or all the way down. It's a combination of the two, right? And sure, we can express the sum of those two as this thing angled downwards, but really we can break this down into a certain length of horizontal and a certain length of vertical, where the length corresponds to the force, right? So what I'm trying to say here is that if he was pulling down, like straight from under the pulley, then his vector would just be straight down. If he was pulling like at a 180 degree, just flat to the top of the pulley like this, then his vector would just be that thing. But because he's not doing it completely vertical or completely horizontally, it's a mix between two things. And they're asking you to solve what is the mix of those two things, right? Which means that choices 3 and 4 have to be wrong, right? Because he's pulling downwards. Here, it's saying that he's pulling upwards, right? This says that he's exerting a vertical force, right? There's a vertical component to this, which is false. Here, he's pulling across and then down. So our answers, the perpendicular components, the things that add up, have to be pointing to the right and down. So now we're left with choices 1 and 2. How do we differentiate between these two? Well, we can just draw our vector. Remember the parallelogram method? Draw a parallel line at the bottom, and then draw a parallel line at the bottom, right? And at their intersection point, draw a line connecting the corner outwards. And let's do the same thing over here. So when we add these two components together, the sum of his total down force and horizontal force, we get these two little calculations, right? And now, which one looks more closer to what he was doing? It has to be choice 2, right? Because when you sum both of those up to get the resultant force, or the resultant vector, it's a lot similar, right? This is way more downward sloped, right? If number 1 was the answer, then F would have to look something like this, right? But here you can clearly see that he's pulling horizontally more than he's pulling downwards, which means that the horizontal component of his vector has to be longer. Number 11 says, which graph best represents the relationship between the mass of an object and its distance from Earth's surface? Mass is always constant. Mass is measured in kilograms, right? And it's never, ever, ever going to change. Your weight is going to change from planet to planet and your distance from Earth, but your mass is always going to be the same, right? People in orbit experience weightlessness. They don't experience masslessness. They still have mass, but they have no weight because there's no gravity in space, right? But mass always stays the same because mass is always conserved. So moving on to number 12, it says a compass is placed near a strong magnet bar as represented in the diagram below. Which diagram best represents the direction of the compass needle? Okay, so how does a compass work? A compass works by highlighting the flow of a magnetic field, right? And how does a magnetic field flow? A magnetic field flows from north to south always. Always. And it's always going to originate from the top of the north and ends up in the bottom of the south. And it's going to follow this kind of, if I draw arrows to represent its path, it's going to follow this path right here. This is the field. And it's going to continue to do this and continue to do this, right? There's going to be a bajillion of these lines. But the point is that it faces out from north, it turns, and then it goes all the way and then turns again to go back into south, right? So from north to south. So if we think about this, if the magnetic field is going from north to south, and our compass points in the way that the north points shows the direction of the the magnetic field, the answer choice has to be 3, right? The north faces the direction that the electricity is flow, that the magnetic field is pointing. So in order to get from N to S, I need to first go forward and then turn. So this compass would be showing that the magnetic field is pointing out from north before it starts turning to S, right? Choice 4 would be wrong because that would mean that the magnetic field is coming into north, which is always wrong. It's always coming out from north. These two are also wrong because the force is going outwards, right? And the force after it passes the compass either goes up or down, right? So these would be wrong because you forget about the other side of the magnetic field. So now moving on to number 13, it says, as Earth orbits the sun in its elliptical orbit, the gravitational force between the sun and the Earth is always attractive, right? Gravity is always attractive. Number 14 says, or asks us, which unit is used to measure the work per unit charge required to move a charge in an electric field? So here they're asking you for a unit that measures work divided by charge. Let's look at our reference table. So we're going to go to electricity, which is up here, and we're going to just look at this. Oh, look, it's voltage. W stands for work, and Q stands for charge. This is asking us work per charge, work per unit charge, work over charge, right? Here is work over charge, W over Q, which is V, or a volt. All right, so moving on to number 15, it says a diagram below shows a negatively charged sphere and point P located within the electric field produced by the charge on the sphere. So now here on 12, we were dealing with magnetic fields. Now over here, we're dealing with electric fields. And with electric fields, you need to remember 2 things. When you have a positive charge or a particle with a positive charge, the electric field points out from the particle. It points outwards from the charged particle. But when you have a negatively charged particle, the electric field goes towards the negatively charged particle. And that's the biggest difference. How can you remember this? Positive people are positive and they want to give support and they want to spread positivity. Negative people are self-centered. They suck, right? So this is a negative sphere, which means that its electric field is going to be pointing towards it. So it's going to look something like this. This is electric field. Oh, so self-centered, so negative. And it's always going to point towards itself, right? So the electric field at point P has to be pointing towards D, right? Because from P, the arrow has to go towards the negatively charged thing. So number 16 says 2 point charges Q1 and Q2 are initially a distance D apart. Which change will cause the greatest increase in electrostatic force between the 2 point charges Q1 and Q2? Okay, so what is electrostatic force and how can we calculate it? Well, it's going to be in the electricity tab and it's going to be this formula right here, Fe. So force electric is pretty much what that says. And it's saying that it's KQ1 Q2 over R squared. So Fe, or force electrostatic, is equal to KQ1 Q2 over D squared. Okay. And I guess I'll zoom in to make it clearer. So KQ1 times Q2 divided by D squared. Okay, so think about it. If I have Q2, this will make my electrostatic force decrease, right? Because I'm decreasing my denominator, right? To get the biggest possible number, I want either my denominator to be the smallest possible number or my numerator to be the biggest number. So that means that doubling d also has to be off the table. Because think about it, if I double d, that means that my denominator is greater, and then I'm dividing my numerator by a greater number, and I get a smaller number as a result, right? Say that k q1 q2 is equal to 2 when you multiply it all out, and my distance is equal to 2. 2 squared is 4. So my electrostatic force is 1/2. But if I double d, right, 2 times 2 is 4, and now 4 squared is 16. So 2 over 16 is like 1/8. So I went from 1/2, which is 0.5, to 1/8, which is like 0.125. So I actually decreased by a lot. Okay, so now that leaves us with either doubling Q1 or having D. And the answer here has to be having D, right? Because D is squared. And if you have D, you're dividing by a smaller number, which means that you're going to have a larger output, right? For example, let's say that kq1, q2 is equal to 1. 1 divided by d squared. Let's say our d was originally 1. So 1 over 1, so our force electrostatic is equal to 1. Now let's say that we reduce our d to 0.5 or 1/2. So now we have 1 over 0.5 squared, or 1 over 1/4, which is now going to be 4. So because we halved our distance, our electrostatic force increased by a magnitude of 4. And if we just doubled Q1, it would only increase by a magnitude of 2. Okay, so number 17 says the diagram below represents two identical conducting spheres. Which statement could be the correct explanation for the charge distribution on the actual spheres? Right, so what do we see here? We see that this side and this side are both positively charged, and the backs are negatively charged. Here's another thing that you need to remember about electricity. Likes repel. If you have a positive and a positive, they will run away from one another. They do not want to be close together. Same thing with a negative and a negative. If you have two negatives next to each other, they will repel against one another. But if you have a positive and a negative, they come together. Okay, so what can cause all of this positive buildup here and all of this negative buildup here? A, is it a small positively charged object between sphere A and sphere B? If there's a positively charged object, likes repel, right? So this positive charge would scare away all the pluses on both sides, right? So this would not work because there would be repulsion. The pluses would then move to this side and they'd congregate here. Okay, now 2, a small negatively charged object is located between sphere A and sphere B. This is false. This is actually true, right? This is fine. I meant to say fine. Because if you have a negatively charged object, the negatives are going to be repelled towards the ends, and the positives are going to be attracted towards the negative. So the answer for 17 has to be 2. Moving on to number 18, it says that the diagram below represents a circuit containing a battery, 2 operating lamps A and B, and 4 closed switches S1, S2, S3, and S4. So this circuit is in parallel, which means that the electricity follows this path right here. It can go and it can go. It could go to the battery. From the battery, it continues on, and it closes back into the battery, right? So it leaves the battery, goes to the lamp, goes back. Now, a part of that electricity also extends onto lamp B. It extends, it goes to the battery, it goes from the battery to lamp B, from lamp B, back here, it meets up with this electric charge. So if you cut switch number 4, or if you open switch number 4, get rid of this connection, guess what? The electricity is still flowing through lamp A. If you open switch 3, guess what? The electricity is still running through lamp A, right? The electricity is equally divided between these two rectangles, right? The electricity runs through this rectangle, and then it also runs through this rectangle, right? But the key thing is that this electricity originates from this path, right? So if you cut anything along this line, lamp B will stop working, but lamp A works just fine because the electricity it divides itself amongst these two different paths that it takes. Now, if you open up switch 1, right, lamp B would still turn on because guess what? The electricity can't pass through here, but it can still carry on. It can still carry on through switch 4 and into lamp B. So if you open up switch 1, everything would be turned off. Sorry, switch 1. I circled switch 4. But if you turn off switch 1, why would that turn everything off? Okay, let's think about it, right? If I'm electricity, I can take one of two paths. I can either go this way to lamp A and loop back to the battery, or I can go this way all the way to lamp B and back to the battery. But the thing is, I always pass through this kind of hallway in order to get back to the battery. If this is opened, I can no longer get back to the battery, so nothing is circulating. Number 19 says, what is the resistance of a 100-watt bulb when operating a potential difference of 120 volts. So here we're asking for resistance. So resistance is equal to what when we have when we're dealing with watts or power, right? Power in volts. Okay. So let's look at something that has power, volts, and resistance. So here we have P, which it represents electrical power, which is which is watts, right? So we're going to be looking at this long chain of equations here. V times I, are we given current? We are not given current. We are given PV, and we're trying to find R. Well, look here. We're given P, we're given V, and we're trying to find R. So here I can use that P is equal to V squared over R to solve this. So P is equal to V squared divided by R. Here we know that we have a power of 100 watts. Whenever you see watts, think power. So here I have 100 is equal to, our potential difference is just voltage. So 120 squared divided by our R. And if you calculate this out, right, multiply by R on both sides and divide by 100 on both sides, you end up with answer choice 4. Great. Okay, so now we're moving on to number 20. I hope this made sense. Pretty much whenever you're unsure about something, always write down what you're trying to solve for. Here we try to solve for resistance given our power and our voltage. So all I did here was I looked for what had power, voltage, and resistance, or all those letters combined. Number 20 says the interaction that is most responsible for binding 3 quarks together in a proton is called strong force. That you just need to know this, right? Memorize it. Strong force. Number 21 says one example of a force doing work is the force exerted by what? Well, what is work? If you don't know what work is, let's go look at a reference table and let's find it out. It's going to be in mechanics, I'll tell you that much. And work is going to be represented by what letter? Let's look for it over here. Work is going to be capital W. So let's look, capital W, or work, is equal to force times distance. So in order for something to work something, you need to multiply a force by a distance, or you need to apply a force over a distance. So in Earth on a high diver falling towards a pool from a platform. Okay, so where is Earth exerting a force on the high diver falling towards a pool? Let's think about that. In this situation, it is, right? Because think about it. Earth is exerting what force? It's exerting gravity, right? So this diver guy goes up, he climbs up to his diving thing. He's on here, and all of a sudden, he jumps off the diving thing. As he's falling, is he traveling distance? Yes. Let's say that this is a 20-foot tall diving board. As he's going down, he's traveling 20 feet, right? So we have distance. And what's our force here? Our force here has to be gravity, right? G. And Earth exerts gravity on you. So yeah, this does have work, right? Because you're exerting force, which is gravity, over distance, how tall the diving board is. Number 2 says a hook on an engine held stationary. This is automatically wrong. You need a force to be applied over a distance. If something is stationary, its distance is not changing. Frictionless puck moving across at a constant velocity. If you have a constant velocity, your net force, or your F net, is 0. And a weightlifter holds a barbell motionless. Motionless, you need motion for work, right? So no. Moving on to number 22, it says a ball falls freely from a rooftop to the street below. The ball starts from rest with 20 joules of gravitational potential energy with respect to the street. The total mechanical energy of the ball just before it hits the street is what? Okay, so what does this mean? Energy is conserved, right? And you have 2 different measures of energy. You have something called gravitational potential energy, which means that how much energy the object has the potential of exerting. So this ball, when it's at rest, has the the gravitational potential energy of 20 joules. Right, it is able to generate, or it stores 20 joules within itself because it is high up. And if it were to drop, it would release 20 joules of energy, right? So GPE, which I'm just going to call this gravitational potential energy, at the top of a summit is always going to equal to the max, and your mechanical energy, or your ME, is going to equal to 0. So this is going to be the max, and this is going to equal to 0. Now, as you start moving, your gravitational potential energy is decreasing because there's less distance between you and the ground, which means that there's less distance for gravity to act upon. And when you finally reach the ground, all of your gravitational potential energy, every single piece of energy that gravity could have accelerated you by or worked on you by, is now gone. You're now at the bottom of your path, and now you're at such a high speed that your mechanical energy is equal to your gravitational potential energy. So all you need to remember here is that at the top, gravitational potential energy is going to be the biggest. At the bottom, when you hit the ground, gravitational potential energy is equal to 0, and mechanical energy is equal to the max. So at the peak, at the very, very peak, mechanical energy is equal to 0. All the way at the bottom, mechanical energy is equal to max, and gravitational potential energy is equal to 0. But the thing is, you start with 20 joules, you end with 20 joules. The energy has to be conserved. Number 23 says, which statement describes the gravitational potential energy P, kinetic energy K, and internal or thermal energy Q of a wooden crate as it is pushed across a level classroom floor at a constant speed? Well, think about what we just said. Gravitational potential energy occurs when you have height. But here, you don't have height, you're on the floor. Right? There's nothing for you to drop by. So your gravitational potential energy is always going to stay the same, right? So your PE is going to remain the same. Next, we have to deal with the other variables here, right? It's going to say that either your kinetic energy decreases or your kinetic energy is going to remain the same. Well, think about it. Your kinetic energy is going to decrease because as you start dragging this crate along the floor, that kinetic energy is going to be converted into frictional energy, right? Why is it hard to push something across a floor? Because the object that you're pushing across the floor generates friction with the floor. And the more and faster that you move this object against the floor, the greater that resistance or that friction is going to affect the movement, right? So you need to put in less and less energy because more and more of that energy is going to be converted into friction. So you could really eliminate this by saying that, or by realizing that because it's on a flat surface, there's going to be no instance of gravitational potential energy, right? So it's never going to change. But your kinetic energy is going to change because you have friction, and your friction is going to increase the more you push something. So moving on to 24, it says the oscillation of elevators up and down a metal antenna produces waves. These waves are what? Well, think about it. The oscillation, which means that you're dealing with a wave, right? And electrons are moving up and down. When you have electrons moving up and down, that's going to be called something called transverse. So number 1 and 4 are off. Longitudinal waves are going something that goes left to right. Transverse up and down. How do you remember this? Longitudinal means long and long is flat, right? Think about it that way. And up and down is tall. So are these electromagnetic or mechanical? These have to be electromagnetic and transverse because electrons produce electromagnetic waves. Okay, 25 says the diagram below shows a incident ray reflecting from a plane mirror. What is the angle of reflection? So let's think about it this way, right? Here is the axis of reflection. This is the line at which it was reflected about, right? Here we were hitting this point at a specific angle, and then we were reflected by the same amount on the other side, right? So the angle of reflection is whatever angle I added to this initial angle to get this other thing on this other side. And oftentimes the angle of reflection is just going to equal to half of the total angle that in change, right? Or it's going to just equal to half of the internal angle. Here the internal angle is 84 degrees, which means that the angle of reflection has to be 84 divided by 2, which is 42 degrees. And what that means is that this light originally came in at an angle of 42 degrees. And then it got reflected by another angle of 42 degrees. And when you look at this all in one, 42 plus 42 is 84. So really, these two sides combine to make this 84-degree reflection. But in reality, it only got reflected by 42 degrees because it was already coming in at an angle. It was something which is added onto that angle. 42 degrees were added on. Number 26 says a characteristic common to both sound waves and X-rays is that they both what? So yeah, I guess it could be true that they travel fastest in a vacuum, maybe, but we don't know that yet. This would actually be false because sound waves travel fastest when you have a lot of medium, right? When you have a lot of particles in the air, and specifically like thick air. That's why sound doesn't really travel that well in space, which is a vacuum, right? Because there's no particles for it to transfer through. Number 2 says causes particles to vibrate in directions parallel to the wave's direction of motion. This is false because sound waves are longitudinal, right? Versus X-rays are transverse, right? So X-rays go up and down and sound waves go left and right. So it's not parallel to the direction of travel because the direction of travel is this, but here they're moving up and down. So this is going to be perpendicular. So 3 says transmit energy without transmitting matter. This is going to be the correct answer simply because a sound wave, X-ray is not mechanical, right? That's a light wave. And 3 is right because both of them do transmit energy without really transmitting any matter. They're just waves. They have like very little mass. Number 27 says the diagram below represents a wave moving to the right of a rope. The point P in the rope is moving towards the what? So the trick here is that you first need to identify which way the wave is moving. If the wave is moving to the right, then your P or your point is going to move to whatever that is behind that. So for what I mean here is when you want to figure out if P is moving up or bottom, you first need to realize or recognize which way the wave is waving. So here the wave is going towards the right, which means when I look at P, I look at the point or any points to the left of P or in the opposite direction. I notice that in the opposite direction, it goes up, which means that P has to go up. So it has to go to the top of the page. So for example, if this question said that the wave was moving this way, I would all of a sudden then have to look at the point, not in the same direction, but the direction before, in the opposite direction. So here, if the wave is traveling to the left, I look at any points to the right. I look at any points to the right and I see that those points are lower than the current P, which means that my P has to decrease or go down along the wave. Here, we're going to the right, which means that in order to figure out the direction that P is traveling, I need to look at the points in the opposite direction. So if we're going to the right, I need to look at the points to the left, and the points to the left are increasing or going upwards. So it means P has to go upwards as well. Number 28 says, what is the wavelength of a 300 hertz sound wave in air at standard temperature pressure? Right, so you know that the velocity of a wave is going to equal to lambda, which is the wavelength times its frequency. So lambda times hertz. Okay, and how do I know this? Because we're dealing with wavelength and hertz. When we look at a reference table up here where it talks about waves, it's the only thing that has hertz or frequency. I guess hertz is the unit, right? But really, the symbol is frequency. So this is the only thing that has lambda, frequency, and velocity all combined in the entire waves tab. Now you may be asking, well, we know the frequency, right? But do we know the velocity? Yes, we do know the velocity because look, if you scroll all the way up, they give you the speed of sound. The speed of sound in air at STP is 3.31 times 10 squared, or 331 meters per second. So now all you have to do is set this equation up. Velocity, which is on your reference table, because it tells you the sound at STP, you go here and you say sound at STP. So 331 has to equal to a wavelength, which is unknown, times the frequency, which is 300 hertz. So you divide both sides by 300 and you get 331 divided by 300, which is going to be 1.01 meters. Moving on to number 29, it says, in a diagram below, a remote control is aimed at a television. When a signal from the remote reaches the sensor on the television, the signal will most likely be partially absorbed and partially reflected. This happens all the time, right? You're never going to have a laser beam or a particle or a wave that's going to be 100% absorbed. Most of the time, it's going to be reflected or refracted off of the screen. That's just how physics works, right? You can't be completely reflected or completely absorbed because it's not perfect. It's just a consumer television. And if it was neither reflected nor absorbed, that means that remotes would never work, which is false, right? It's going to be partial. It's always going to be partial. So now moving on to number 30, it says, compared to the waves of blue light traveling in a vacuum, the waves of red light traveling in a vacuum have what? Well, here we're talking about different colors of light. So we go into our electromagnetic spectrum and we see where we find colors. So it's going to be somewhere here. It says that waves of red light traveling in a vacuum have what compared to blue lights? So let's look at this. Here we have blue. So here we have red, right? This is orange, and here we have blue. So notice how the frequency of blue is higher, right? So if the frequency of blue is higher, that means that red light has to have a lower frequency, right? And it has to have the same speed because everything travels the same speed in a vacuum. So that's all you need to know. You really just need to realize that red has a lower frequency because here it's being raised to the 14th. Here you have 3.84 times 10 to the 14th, and here you have 6.10. So the frequency of blue light is larger, but just note that all of this travels at the same speed in a vacuum. Number 31 says, earthquakes often cause buildings between 12 and 40 stories high to vibrate at an amplitude high enough to be destructive. Buildings are often designed to absorb this vibrational energy that might cause them to vibrate at their natural frequencies. right? This tendency for an earthquake to cause a building to vibrate at a large amplitude is a result of resonance. Here, natural frequency gives this away, right? Resonance is is kind of a phenomenon where every single object around you has this magical frequency at which it starts to break, or at which it starts to match that frequency. So, for example, an opera singer can break glass because of the resonance effect, right? Here's our wine glass, right? And we're looking at this from a top-down perspective, right? If once the lady starts singing, right, she sings at such a frequency that these sound waves kind of bounce in and out of the glass and make the glass start to like change shape. It starts to squeeze the glass in, narrow, and outwards wide, and narrow again, and outwards wide, and narrow and outwards until it shatters, right? So natural frequency always refers to resonance. 32 says, during the radioactive decay of uranium-238, a thorium-234 atom, and an alpha particle are produced. During this process, there is a conservation of both charge and mass energy. The world will always, always, always conserve charge and mass energy. Right here, what was conserved? Charge was conserved because alpha particle was produced, right? Mass energy was also produced because guess what? Uranium didn't decompose into thin air. It decomposed into another object that also has mass. So number 33 says an antiproton has a charge of what? Well, what is a proton? A proton is a state of matter, and it's a baron, right? So it has 3 quarks. Protons have quarks up, up, down. So if you want to find the charge of a proton, you just need to add 2 up quarks and a down quark. So an up quark is going to be 2/3. So 2/3 times 2, or 2/3 plus 2/3, is going to be 4/3. And now a down quark is going to be -1/3. So 4/3 plus -1/3 is equal to 3/3. So because we knew this up, up, down configuration of a proton, we now know that the charge of a proton is going to be 1, or plus 1e. Now here it's asking us for the antiproton. If we look at this, it says for each particle there's a corresponding antiparticle with a charge opposite of that associated particle. So here, whenever you see anti whatever you see in the front, just switch the sign to the opposite. So because I have positive 1e, I now have negative 1e, which is choice 4. Moving on to number 34, it says 2 pulses approach each other in the same medium. Which pair of pulses result in the largest amplitude displacement of the medium as the pulse passes through each other? So choice 1 and 3 are both out because 1 and 3 will both cancel each other out. If you combine this with this, you will just get a flat line because the distance up is equal to the distance down. The same thing with 3. It just flipped. This will fill in. It will fill in this hole. You'll once again be left with a flat line. So now we're left with 4 and 3. Okay, cool. So if these 4 combine, notice how they're both on the right side and they're both heading in each other's correct direction. They will simply just add, they'll stack. So the amplitude will be doubled to like something like this. But here, now we stack on top of an even bigger stack, right? These 2 are both facing the same way, heading the same way, which means that they will not interfere with one another. They're also both negative and in the bottom direction. So when these 2 combine with one another and add to one another, this entire thing is going on the top of this wave, which is smaller than choice 4. So number 35 says 2 waves of a similar wavelength interfere to form a standing wave pattern as represented in the diagram below. What point on the diagram represents a node? The point has to be D because nodes is where these crossovers happen. And that's all of question 35 for the Physics Regents exam. Part A gone over. If you have any questions, please let me know in the comments section below. Otherwise, if you want to like, comment, and subscribe on this video, it really does help with the channel. It helps motivate to make more videos. But I did hope you learned something. If you have any questions, feel free to ask in the comments. Hope you all have a nice night.